Hi there. Have you ever wondered how video game levels are made? Yeah, me neither, but this paper has. And in this paper, you can see a reinforcement learning agent that has learned how to make video game levels in various ways. So this is implemented for this game here, where the goal is simply to make the longest maze. This game here is an adaptation to The Legend of Zelda, where you have to get a key to the door. And this game here is called Sobokan, where you have to put all of the crates onto the green squares in order to solve it. So it's a puzzle game. All right. And this is done via reinforcement learning. So the paper we're going to look at is called PCGRL, Procedural Content Generation via Reinforcement Learning by Ahmed Khalifa, Philipp Bontrager, Sam Early, and Julian Togelius. Now this paper is basically just a fun paper, and I feel, and it shows how to frame a problem in terms of reinforcement learning and then how to solve it. It's pretty straightforward, it's fairly short, and the code's available and all, so you can go check it out yourself. They say, we investigate how reinforcement learning can be used to train level designing agents. Okay, so usually we do reinforcement learning for playing games themselves, and now we use reinforcement learning to train an agent that can design a level. So we don't design the level itself straightforward. We design the agent that designs the level. And what's the advantage here? The advantage is, of course, the agent could then potentially generate multiple different levels once we have trained it. I say this represents a new approach to procedural content generation in games where level design is framed as a game itself. So the design of the level is now the game. And the content generator itself is learned. By seeing the design problem as a sequential task, we can use reinforcement learning to learn how to take the next action so that the expected final level quality is maximized. This approach can be used when few or no examples exist to train from, and the train generator is very, very fast. Okay, so this is the outset of the problem formulation. Now we're going to go through the steps you have to do in order to make this work. There are a few things that I think this paper does quite well, and so the first thing is you actually have to frame the problem in terms of reinforcement learning. So what is reinforcement learning? It's pretty simple. In reinforcement learning, you have this agent environment split. Okay, so at each step, the environment is going to send the agent an observation. So the environment is going to send an observation to the agent, and the agent needs to take an action in response to that. Now, something happens in here. We don't worry about that, and the environment is going to send the next observation. Okay. That is a result from taking this action, and it is also going to send the reward for this action. So at each step, the agent gets an observation and a reward for the last action it took, and it has to output the next action. Now the environment, of course, has to somehow decide, how do I represent the observation? This is the representation. How do I transform one observation to the next observation given an action? Okay, the action comes in and transforms the last state to the next state. And then how do I give the reward? How do I calculate the reward? So these things are the things you have to decide on. The observation space, how the reward is calculated, the action space, and how an action transforms one representation into the next representation. So this is what we're going to look at, the different variants. We're not going to look at specifically how reinforcement learning is done, because once you have an environment like this, you can just plug it into a standard reinforcement learning algorithm and it will solve it for you. Okay, so that's the power of basically having standardized or representations. So the observation space of this problem is going to be pretty simple. All the games we're dealing with here are in this, I already did some drawings, are in this framework of this grid world game. Okay, so you have this grid. This level is subdivided into this grid, and that naturally corresponds, of course, to a 2D matrix. Now, each point in this matrix has a number, and the number describes what type of tile this tile is. So as you can see right here, the 1 is going to be a wall, while the 0 is going to be empty space. 3 here is one of these crates, and 2 is the player. So you get the point, right? Each number corresponds to a type of tile. So far, so good. That's the observation space. Now, what is the action space? What the agent can do? At each step, they say the agent can change one of these tiles. Okay, so it can change one of these tiles. Let's say this one right here. It can change it to a different one, or you can just leave it. So this is a wall right now, and it makes the problem fairly interesting to have a wall right here in the middle. So since we're looking at this tile, we might just want to leave this right there. We could also change it. We could actually change it such that to a 2, such that there is another player right here. Right? Can I even draw this? This yellow isn't. Such that there is now 2 player tiles in the game. This would, of course, be an invalid level, and the reinforcement learning agent ultimately should learn to produce valid and good levels. Okay, so at each step, you can change one tile, and of course, the goal is to make a better and better and better level over time. Now, how do you choose which tile to change? That's a thing you have to define, and they define 3 different ways in which the agent can choose which tile to change. In the narrow formulation, they themselves, so the environment chooses the frame, the tile to change. So the environment will say, now you can change this tile if you want. And then the next step, it will say, now you can change this one if you want. Now you can change this one if you want. Now this is completely random, okay? How the environment chooses. Actually, it doesn't have to be, but the environment chooses, and that is problematic for the agent because the agent cannot kind of predict which tile it could change next, and therefore it cannot really plan ahead how it wants to change the level. It can only make very, very local, very greedy choices. It can be like, oh, I'm right here. I might actually build a wall right here. Yes, that seems good, but it can't. So an example is maybe you want to make the level more interesting. Maybe you think that the crate up here is a bit close to this field here. You have to push it onto this field, and that's fairly easy, right? So you just push it like up and then to the left. Actually, it's not that easy because there's the wall right here, and you have to go around. Actually, you'd probably have to push this down. But let's say the level is too easy, and you want to move the crate to a bit like, let's say here. In this framework where the environment tells you which tiles to change, you can basically, once you come across this tile, you can delete it. Okay, but then you kind of have to wait and wait and wait and wait until at random this tile where you want to put it is selected. And this might actually never happen because the episode might be over, and if it never happens, you are in an invalid level, right? So the agent here is basically forced to greedily make the level valid before it can make it interesting, and then it can only make it interesting in sort of local ways. So the second way that the second formulation here is the turtle formulation. Now, you might know this from the turtle graphics, where basically you have this little turtle thing, and you can always move it either like, down, up, left, or right, and then you can always put a dot or not put a dot, and thereby you can like trace out things. This is like intro to programming. Same here. So now the agent is given a starting square, and it can choose to change it or not, but it can also choose how to move to the next square. So to the right, up, left, or down. It can choose. So it can go along and say, okay, now I'm here. I want to change it to a 2. Now I'm here. I want to change it to a 2. Now I'm here, and so on. So it can basically do things like build long walls and things like this. So it can plan ahead more considerably. But still, if you regard the problem from before, if it wants to place the crate to a different location, it can, like if maybe it's here, okay, the agent is here, and then it can say, okay, I want to not change but move, not change and move, not change, move, and then it can delete, and then it has to move over here step by step until it can place it again. So it can plan ahead considerably longer. Actually, it could just move straight over because the agent itself is not constrained by walls. So it can move ahead quite a bit, but it's still kind of localized changes because it can move one tile at a time, right? And if in between the episode ends, it's again an invalid level. So the third formulation is the most powerful formulation. It's called the wide formulation. And this is where the agent at each time step can not only choose how to change the tile, but can freely choose the next tile to change. So it could say in one step, it could say, I want to delete this tile. And then in the next step, it could say, I want to place it right here. Okay, so it can plan ahead considerably. So how you design the action space is very important for how your agent, or for what your agent can possibly learn, and how easy it is for the agent to learn, because it's going to be pretty easy for this agent to learn to move crates like this, where even though the other agent that moves one tile at a time can also do it, it has to plan ahead for longer. So it has to sort of invest more of the reinforcement learning power into doing these sorts of things. But of course, it's being more constrained also means you have less actions at your disposal. Like this last agent, it has a lot of actions it can do. It can choose any tile at once, right? So that can also introduce considerable exploration dilemma. And you have to trade these things off when you design things like that. All right, so this is the action space. Now, how the observation evolves into the next observation should be fairly clear. I mean, that's already given by the action space. If you ask yourself, if you're in this situation right here, and the agent deletes the crate, then the crate is no longer there. So if it changes this to a 0, then it's just empty space now. Okay, so that's fairly obvious here. Now, the last thing we need to do is the reward calculation. What reward do you give the agent? And you can give the agent the reward either, let's say, at the very end. You cannot give it a reward for the entire episode and give it a reward at the very end. Reinforcement learning algorithms are able to deal with this to a certain degree. You can also decide to give it at each step. Now, the way they do it here, I believe, is they give it at the end, and they have multiple components to the reward. So the reward in this case is how well the level fulfills certain goals that the programmer sets. So the goals in Sobocon are basically the rules of the game, and that means there is only one player. If there are two or none, then the reward is less. There are at least one crate, and there are as many crates as green fields. Okay, so here you can see there are only 2 crates, but 3 green fields, so the agent will get a penalty for producing a level like this. And then the last thing is the level has to be solvable. And for checking solvability, the authors of this paper simply employ a Sobocon solver. They have a Sobocon solver that is like a tree search algorithm that tries to solve the level. If it can't solve the level, then the level is invalid and the agent gets a worse reward than whenever the level is solvable. Okay, so how you design the reward is also very important. If you only give like a 1 reward when all the goals are fulfilled and give a 0 reward as soon as one of the goals is not fulfilled, a reinforcement learning agent is going to have a very, very much difficult time to learn that. So you have to kind of design the reward such that you help the agent realize what's important. So maybe if there's only 1 crate missing, but in fact the level is solvable, except for that, that maybe 1 green field is going to be empty, then you could still give a fairly high reward, but you could just give a higher reward when the level is actually solvable, or all the rules are fulfilled and there is a crate here. Okay, The other thing to notice here is that in this case, you actually do need a solver for the level, since it's a puzzle game. And that means your agent is only going to produce levels that are as difficult as your solver can solve. So that's going to be a considerable problem. But that's, a limitation here. But all of their rewards are hard-coded, so to say. So the reward is given by the environment. So now that we have observations, which are these matrices right here, we have actions, and we actually have 3 different ways of formulating actions, and we have reward. They can simply plug this into a standard reinforcement learning algorithm. Now they have one last thing that they have, which is this change percentage parameter. So what they say is they give the agent an initial state, and then the agent is allowed to change it around, like here. So on the left, you have this initial state. Okay, this is sort of a random initial state, and you allow the agent now to change it in this stepwise fashion, and you always update the agent. By the way, the agent, as you might imagine, the agent takes this matrix right here and shoves it through like a few convolutional layers and then decides on an action. I'm almost forgetting that this is so obvious by now that the agent is like a standard deep learning, taking in a 2D, doing some convolutions, and then having like a policy output. So you shove this into a proximal policy optimization algorithm, which is a standard reinforcement learning algorithm, and you allow it to change these things. Now, what they do is they only allow the agent to change the levels by so much, because what they say is if we start out from these different states, you can decide on 2 things. Either you can train the agent to find you the best possible level ever, right? But then it would sort of ignore the starting state. It would just learn which level gives me the highest reward, and it would just change all the tiles always to that, right? It would just try to to always reach that best possible state and forget the start state. So they say, okay, the last constraint is the agent can only change like 20% of the tiles at most. And after that, we end the episode, or we just don't allow the agent to change anything anymore. It needs to first, so if it changed this here to empty space and wants to change something else, it first needs to change this back, and then it can change something else. So you can do that. So this constrains the agent and kind of teaches it that in order to get a high reward, it must sort of adjust the starting state to something that gets higher reward. And that's one way of making the levels that you generate more diverse. It's sort of a unique problem to this particular kind of reinforcement learning problem, because sometimes, like most of the time, you just want to find the highest reward, whatever. But here you also want to, maximize diversity of the levels you generate, and therefore you could say that's a pretty good constraint to put into that. So that's a thing I like here about this paper, this change percentage constraint. Now at inference time, you can change that. So at training time, you only change 20%, but at inference time, you can technically let the agent run for longer. As you can see, I think here they just let it run until it finds something good, like this one right here, fairly good from this starting state. And you can see it sort of still adjusts to the starting state right here. So you can see that it connects the 2 dots on the top. So the goal is to make the longest possible maze, or a long maze. So it connects these 2. You can see here also this one connects them. And then it goes out here and connects to this one. So it's fairly good at relying on this starting state. Now you can see that these turtle and wide representations that can actually choose where to go and where to change something are considerably more powerful than this narrow thing, especially if you look at this level right here, which again is the importance of designing the action space well, is going to directly affect the outcome that you're going to have. All right, and you see the same thing here for this Zelda game. Now, here you can see the starting state often involves, let's say, Here you have 2 players and you have 3 keys, and that's an invalid starting state, and sometimes the door cannot be reached. Sometimes the door is actually not even there, like here. And you can see that all of the agents sort of learn to make at least valid levels, where you have the player and the door and the key right here, being able to reach everything. So that's, fairly cool, because counting is one of these things that the neural networks aren't necessarily super good at. So it's nice to see that, they can here they have 2 players and they're deleting one of them. Here they have 3 crates, and they actually make it such that the number of crates and the number of green tiles agree. So, that's fairly cool that this comes out. And here you can see the different power of the algorithms. So in this binary problem, and this is the Zelda problem, this is Sobocon problem, you can see that as you allow the agent at inference time to change more and more of the level, the percentage of levels where the agent gets a good level, like succeeds in building a valid level, goes up and up. And now this, as I already said, this narrow representation here appears to be a bit less powerful than the others. Interestingly, in Sobocon, the best one is this turtle representation, where you can only change 1 tile at a time, and not the more powerful wide representation. It's probably because, I'm going to guess that's because either the reinforcement learning algorithm isn't powerful enough, or the representation, like the CNN, is maybe misarchitectured a bit. Technically this representation should be able to achieve higher scores, but not as easily, because, as I said, the action space is so much higher. So it's more difficult to learn, but ultimately it should learn it better. All right, so this was this paper. I think it's fairly cool and fairly fun to view it from this particular perspective. And they discuss that the future could be that humans solve this together, because usually when you have assisted level design, you would have some sort of like an optimizer running to optimize the level you're working on directly. Like you'd say, okay, make something here, and it would sort of run for a while, and that takes time. Now this agent at inference time is very, very fast. So it can, work together with humans. So the human would say, for example, oh, here, please make a wall right here, because that's going to make the level more interesting, but make it such that the level is still, interesting and solvable. And then the agent can, go across, do some things that's going to be super fast. And agents and humans could work together at this. Now, one drawback, of course, is that in a puzzle game like Sobocon, you have to make sure the level is solvable. And here, luckily, you can employ a solver, but as the puzzles get more difficult, that's not super, that's not going to be the case that much. And also they remark that most of the levels generated are fairly easy, because their reward only depends on whether or not the level is solvable by an easy solver, right? So you could give some reward for how difficult the level is, but then again, that depends on your solver. So an interesting next step would be to evolve these, or to train these as you train reinforcement learning agents to solve these kinds of games. So kind of do a curriculum learning, sort of a GAN setting between level generator and reinforcement learning algorithm, like reinforcement learning game player, to sort of evolve levels and agents at the same time. I think it's sort of like these poet approaches, except you would directly learn. I think that would be next nice direction for this work. In any case, the code is available. You can even plug in your own games and make your own levels. So check this out. And with that, I'll see you next time. Bye-bye.